Hello and welcome to NCC Group's Cryptopals guided tour. My name is Eli, I'll be your guide. In this video we're going to be looking at Challenge 8 from Set 1, which involves detecting AES in ECB mode. Let's take a look at this input file here. We have a bunch of lines, each line including an individual hex-encoded ciphertext. One of these ciphertexts has been encrypted with ECB mode, the rest have not. Our goal is to identify the ECB ciphertext. We do not need to decrypt it, we just need to find it. And the way we're going to do that is by remembering that ECB is stateless and deterministic. It will always encrypt the same 16 plain text bytes to the same 16 ciphertext bytes as illustrated in this famous picture of the penguin here. You can see that the same input blocks always map to the same output blocks as, for example, in the background of this image or in the black regions here. This, of course, is a major failing of the mode. It is something that you never want to see in an actual crypto system, and it is the primary reason why ECB mode is never used in practice. It is also the way we're going to solve this challenge. Now, in order to look for a ciphertext with repeated ciphertext blocks, we need a way of splitting that ciphertext into blocks. And the way we're going to do that is by defining a new function that we're going to be using a lot in the following challenges. Now let's recall back to Challenge 6. I'll pull it up here to jog your memory, wherein we took conjectured key sizes and then chunked the ciphertext into blocks based on that size. Now what we're going to do here is fairly similar to this, but generalized. Now we will write this as a list comprehension. Rather than doing an explicit tuple of chunks, we will generalize to a list comprehension. We're going to iterate over the start of each chunk, and then we are going to slice our byte string according to the chunk's size. So let's start by setting up our iteration bounds. So this says, let's start at 0, iterate up until the length of the byte string, and go by steps of chunk size. So if the chunk size is, for example, 16, then this will go 0, 16, 32, and so forth until it gets up until the length of the total byte string. Now, for each step in this loop, let's figure out what our expression needs to be. We're going to be slicing into B. We're going to start at our index, and then we're going to slice to that index plus the chunk size. And there we have it. This defines a list of chunks. And by the way, you might be wondering why I'm saying chunks and not blocks here. There is actually a good reason for that. It's possible that we're going to be using this to break ciphertexts into blocks. However, there are cases where the size that we're using is not actually the block size of the cipher. For example, in our repeating key XOR problem, that was effectively a very weak block cipher with a block size equal to the size of the repeating key. And we did not actually know what that size was, and so we had to guess it. If we were using this function to implement the guessing logic, most of the inputs to it would actually technically not be block sizes. They would be chunk sizes. They would give us chunks of bytes which may or may not be aligned with the block size. And so I'm using chunks because it's a more general term here than blocks. It's honestly probably more or less fine to use the two interchangeably. It's not that big of a difference. But for me, I think it's just something that I would prefer to do, to have this little bit of precision in terminology here. And let's make sure to close our list comprehension here. And if we're ever having a problem with this, we can use this quiet flag to diagnose that problem. Like I said, we're going to be using this function quite a bit in the following challenges, so it's just nice to future-proof it a little bit by including this up front. Now let's go ahead and test this function. And rather than testing it on an interactive prompt, we're just going to give it a trial by fire, by which I mean we're going to apply it to the challenge and see if it works. So let's go ahead and define our main block here. And within that block, we're going to start by opening the input file and reading out its contents, which we will then hex decode line by line. Now that we have our ciphertexts, let's go ahead and loop over them. We know from the challenge that our block size is 16 because that's the number that's provided up here in the challenge statement. So we can assume a block size of 16 in our argument to bytes to chunks. And this enumerate function that I'm using here is a very useful little iterator that allows you to iterate over an arbitrary iterable and also get the indices for each iteration. The alternative to this would be to set I equals 0 outside the loop and then to increment I within the loop explicitly. But this is a terser way of doing things that is less error prone. And it also has the ability to recover gracefully. If you rebind I within the loop, it'll be properly rebound to the counter at the top of the loop. Whereas if you were handling I yourself, that would not happen. And you might be wondering what's going on with this line. So let me clear it up for you. A set is essentially like a list or a tuple, except that it is unordered and it can only contain one entry for each of its elements. So for example, if you made a list of the first 4 Fibonacci numbers like so, that list has length 4. However, if you convert it to a set, okay, I tried to get too clever. If you convert it to a set and take the line of that, then that will have length 3. And the reason for that is because the set does inherit a deduplication of elements. This is one very terse way of trimming elements out of a set, and it's what we're going to choose to use here. I'm not sure if it's the most performant way in Python. Off the top of my head, I can't think of a better option. It certainly has fairly high memory overhead, but it might be actually relatively permissible as far as time complexity goes. And in any case, it is certainly readable. So we're going to use this to deduplicate blocks in our chunked ciphertext, and that will allow us to detect when we have a ciphertext with repeated blocks. And as you can see here, we are skipping any line which has 0 repeated blocks, because that is not likely to be using ECB by our heuristic. As a side note, it is possible, it is certainly possible that it is using ECB and just has no repeated plaintext blocks. However, we are assuming here that the plaintext we've been provided is going to have repeated blocks, because otherwise this challenge would be pretty much impossible. So we're just going to go ahead and print out any line that has more than 0 repeated blocks. And let's go ahead and see what we get when we do that. There we go. There is exactly one line that matches our criterion, which is line 132 with 3 repeated blocks. Of course, it is a little bit annoying that we don't get to find out what the actual plaintext is, but we're going to have to live with that. At least we know we've solved the challenge. Well, that does it for set 1. Thank you for watching. I hope you enjoyed these. I hope maybe you found them valuable. And I will be doing all 8 sets of challenges here, so please join me for the rest of the series if that's something you want to do. Thanks for watching. I'll see you on the next one.